It is the summer of 1942 at a British armored repair depot in the western desert of Egypt, where the heat coming off the sand is enough to blur the air and the dust gets into everything, into the food, into the men's eyes, into the engines. A team of mechanics from the Royal Army Ordnance Corps is working on an American-built medium tank, an M3 Grant, that has been pulled out of the line with engine trouble. They have the engine deck open, and they're looking down at a sight that no British tank mechanic had been trained for, because no British tank used an engine like this one. It is not a long, low engine block of the kind that powered British and German tanks. It is a great circular mass of 9 cylinders arranged in a ring, like the petals of a steel flower, like the engine of an airplane. Because that is exactly what it is. It is an airplane engine sitting in the back of a tank. The mechanics know it as the Continental R-975, and they have learned through hard experience in the desert both its virtues and its vices. They have learned that it starts reliably, that it runs smoothly, that it is, in its way, a good engine, and they have learned to curse it because it is tall, which makes the tank tall, which makes the tank a bigger target. Because it is air-cooled, which means it has to be fed enormous quantities of the dusty desert air to keep it from overheating, and the dust eats it alive. Because the lower cylinders, the ones at the bottom of the circle, collect oil when the engine sits, and if you do not turn the engine over by hand before starting it, the trapped oil can wreck it. Because it burns precious aviation-grade gasoline, the same fuel the Royal Air Force wants for its fighters. This engine is a compromise, a workaround, an airplane engine pressed into a job it was never designed to do. And yet, in the summer of 1942, when the German Africa Corps is driving toward Alexandria and the British need every tank they can get, this airplane engine is the only thing keeping thousands of American medium tanks running. It is not the engine anyone wanted, it is the engine that was available. And in a war, the engine that is available beats the engine that is not. To understand why an airplane engine ended up in the back of a tank, you have to go back to the fundamental problem that haunted the entire American tank program at the start of the war, the problem of the empty engine compartment. The United States had designed good tanks, or at least adequate ones, the M3 Lee and Grant, and then the M4 Sherman. It had the hulls, the turrets, the guns, the armor, the tracks, the transmissions. What it did not have, what it had never developed, was a purpose-built tank engine, an engine designed from the ground up to power an armored vehicle. The reason was money, or the lack of it. Between the wars, the American Army had been starved of funds, and tank development in particular had been neglected almost to the point of non-existence. Nobody had spent the money to develop a dedicated tank engine because there had been almost no tanks to put it in. So, when the war came and the United States suddenly needed tanks by the thousands, it faced a tank with no engine. And designing a proper tank engine from scratch would take years that the war did not allow. The Army had to find an engine that already existed, that was already in production, that could be adapted to tank use immediately. It looked around at what American industry was building, and the choices were limited. There were truck engines, but they were not powerful enough. There were no large, powerful, proven engines being built in quantity that were suited to a tank, except in one industry, the aircraft industry, which built large, powerful, sophisticated engines by the thousands. And among those aircraft engines was one that was compact, reliable, well-proven, available, and just about powerful enough. It was the Wright 975 Whirlwind, a 9-cylinder Radial that had been flying in civilian airplanes for more than a decade. The Army chose it, licensed it to Continental Motors for mass production, and put an airplane engine in its tanks, because the airplane engine was there and a tank engine was not. This is the paradox at the center of the story, and it is the opposite of the paradox in the more celebrated tank engine stories. The other Sherman engines, the Ford GAA, the Chrysler Multibank, the GM Twin Diesel, are remembered, when they are remembered at all, as clever improvisations, as triumphs of American ingenuity. The R-975 is remembered, when it is remembered at all, as the bad engine, the compromise, the airplane engine that did not belong in a tank, the one everybody was trying to replace. Every story about the other engines begins with the premise that the R-975 was inadequate and that something better was needed. The R-975 is the villain, or at least the problem, in everybody else's story. And yet the R-975 was the engine that actually carried the American tank program through its most desperate period. When the Sherman first went to war, when American tanks first reached the British in the desert, when the M4 first saw combat at El Alamein in late 1942, the engine in the back of those tanks was the R-975. The Ford GAA was not ready. The other engines were still being developed or were being shipped to allies. The R-975 was the engine that was available in quantity when quantity was what mattered most, and it powered the Sherman through the crucial early battles. Continental built more than 53,000 of them, far more than any other Sherman engine, more than 7 times as many as Wright had ever built for aircraft. The R-975 was not the best Sherman engine, but it was the first, and the most numerous, and the one that was there when the others were not. The story of the R-975 is the story of the unglamorous, imperfect, compromised solution that does the actual work while everyone waits for the better solution that has not arrived yet. And it deserves to be told properly, including the part where we explain, as the popular histories do not, exactly how a radial aircraft engine works and why it was both a reasonable choice and a problematic one for a tank. The popular history, when it mentions the R-975 at all, says that the Sherman used an airplane engine, that this was a compromise, and that the engine was tall and underpowered and prone to catching fire. It rarely explains what a radial engine actually is, how it works, why its shape is the way it is, why air cooling was both its great virtue in an airplane and its great problem in a tank, or why the very configuration that made it compact in one dimension made it bulky in another. It treats the radial engine as a known quantity, a thing the audience is assumed to understand, and moves on. But most people do not actually know how a radial engine works, or why its cylinders are arranged in a circle, or what that arrangement does to the vehicle it powers. So this account will explain it. We will explain what a radial engine is and why its 9 cylinders are arranged in a ring around a single central crankshaft. We will explain the clever and slightly strange mechanism, the master rod and the articulating rods, that lets 9 pistons drive a crankshaft that has only one throw. We will explain why a radial engine is air-cooled, why that air cooling is brilliant in an airplane and troublesome in a tank, and what Continental had to do to make an air-cooled aircraft engine survive inside the sealed metal box of a tank's engine compartment. We will explain why the radial shape forced the Sherman to be tall and why the lower cylinders had a dangerous habit of filling with oil. The goal, as always, is not merely to say that the engine worked or did not work, but to show how it worked, because the mechanism is where the real understanding lives, and because the audience deserves the engineering, not just the assertion. Let us start with the most basic question, the one the popular histories skip. What is a radial engine, and why are its cylinders arranged in a circle? In most engines that people are familiar with, the cylinders are arranged in a line, an inline engine, or in 2 lines forming a V engine. The pistons move up and down in their cylinders, and they drive a crankshaft that runs the length of the engine, with a separate crank throw, a separate offset, for each cylinder. A radial engine is different. In a radial engine, the cylinders are arranged in a circle, radiating outward from a central hub like the spokes of a wheel or the petals of a flower, all in a single plane. The R-975 had 9 cylinders arranged in such a circle. At the center of the circle is a single, very short crankshaft with a single crank throw. And here is the clever part, the part that makes a radial engine possible and that the histories never explain. All 9 connecting rods from all 9 pistons connect to that single crank throw. They do this through an ingenious arrangement called the master rod and articulating rods. One of the 9 cylinders, the master cylinder, has a connecting rod, the master rod, that attaches directly to the crank pin in the normal way, with a bearing that wraps around the crank pin. The other 8 connecting rods, the articulating rods, do not attach to the crank pin directly. Instead, they attach to the big end of the master rod, to a ring of pins arranged around the master rod's bearing. As the crankshaft turns, the master rod swings around the crankpin, and the 8 articulating rods, attached to the master rod, drive their pistons up and down in sequence. The whole assembly, the 9 pistons, the master rod, the 8 articulating rods, all working off a single crank throw, is one of the most elegant mechanical arrangements in the history of the engine. It allows 9 cylinders to drive a crankshaft that is only as long as a single cylinder's throw, which is why a radial engine is so short in the direction of its crankshaft. The engine is a flat disc of cylinders, very short front to back, with all the cylinders firing into a single central point. It is a beautiful piece of engineering, and it was designed for an airplane, where its particular shape and its particular cooling method were exactly right. The radial engine was perfected for the airplane, and to understand why it was a compromise in a tank, you have to understand why it was so right in an aircraft. The radial engine's great advantage was air cooling, and air cooling in an airplane is close to ideal. An aircraft engine sits at the front of the airplane, or in the wings, fully exposed to the airflow created by the aircraft's forward motion and by the blast of the propeller. The cylinders of a radial engine, arranged in a circle, all stick out into this airflow, each one fully exposed, each one finned with closely spaced metal fins that increase its surface area. As the airplane flies, air rushes over and between the cylinders, over all those fins, carrying away the heat of combustion. The engine cools itself simply by being exposed to the wind of the aircraft's own flight. No radiator, no water pump, no coolant, no plumbing, none of the heavy and vulnerable apparatus of a liquid-cooled engine, just cylinders in the wind. This made the radial engine light, simple, and reliable for aircraft use. There was no coolant to leak, no radiator to be punctured, no water pump to fail. The engine was mechanically simpler and lighter than a liquid-cooled engine of equivalent power, and its reliability made it the favorite of the United States Navy in particular, which valued reliability above almost everything for engines that would be operated far out over the ocean. The radial's short length suited it to the front of an aircraft fuselage. Its reliability and simplicity suited it to the demands of flight. The Wright Whirlwind family, including the R-975, was a triumph of this air-cooled radial philosophy. The most famous of all the Whirlwinds, the J-5, had powered Charles Lindbergh's Spirit of St. Louis across the Atlantic in 1927, its air-cooled reliability carrying Lindbergh through 33 hours of solo flight when a single engine failure would have killed him. The R-975 was the larger, more powerful descendant of that famous engine. It was a fine aircraft engine, born for the sky. And then the Army took it and put it in a box. Behind the radial engine was an outsider who had championed air cooling when almost the entire engineering establishment was against him, and his story is the human heart of this one. His name was Charles Lawrence, and he was the man who, more than anyone, made the American air-cooled radial engine a practical reality. In the years after the First World War, the conventional wisdom in aircraft engine design favored liquid-cooled engines, which were more powerful and more refined. The great aircraft engine companies, Wright and Curtiss, were committed to liquid cooling and were not much interested in air-cooled engines, which were seen as crude and limited. Lawrence was a small operator, running his own modest engine company, and he believed, almost alone, that the future of aircraft engines, especially for the Navy, lay in air cooling because of its simplicity and reliability. The United States Navy agreed with Lawrence. The Navy wanted air-cooled engines for its carrier aircraft because an air-cooled engine with no coolant to leak and no radiator to fail was far more likely to bring a pilot home from a flight over the ocean. But the Navy doubted that Lawrence's small company could produce engines in the quantity needed. So the Navy applied pressure to bring about a merger, and in 1923, Lawrence's company was absorbed into the larger Wright Aeronautical Corporation, with Lawrence's air-cooled engine designs and engineering at the heart of the deal. Lawrence himself became a vice president of Wright, and later its president. His air-cooled engine, developed and refined, became the Wright Whirlwind series. The engineer Sam Heron, another key figure, contributed crucial work on air-cooled cylinder design, on the metallurgy and the cooling fins and the valves that let an air-cooled cylinder survive the heat of combustion. Together, these men made the air-cooled Radial a practical, reliable, powerful engine. Lawrence is sometimes called the father of the air-cooled aircraft engine, and the whirlwind that carried Lindbergh across the Atlantic and the R-975 that carried the Sherman into battle were the children of his stubborn, against-the-grain conviction that air cooling was the way. He was the outsider who was right, and his engine ended up in places he never imagined, including the back of a tank. Now we come to the central engineering problem of this story, the problem of putting an air-cooled engine inside a box. Everything that made the Radial engine excellent in an airplane depended on one thing: the free flow of air over its exposed cylinders. In an airplane, that airflow was guaranteed by the aircraft's forward motion and the propeller blast. In a tank, it was not guaranteed at all. A tank engine sits in an enclosed compartment at the rear of the hull, surrounded by armor, with no propeller and no slipstream. The air-cooled engine dropped into this sealed box had nothing to cool it. The very feature that made it brilliant in the air, its dependence on airflow over its cylinders, became its central problem on the ground, because in a tank there was no airflow unless one was artificially created. So, Continental and the Army had to create the airflow artificially. When the R-975 was installed in a tank, a large cooling fan was attached to the engine's power shaft, and this fan was surrounded by a shroud, a metal duct that directed the air the fan moved. The fan pulled air in through openings in the hull, forced it over and through the cylinders in their cooling fins, and pushed the heated air out through other openings. The fan and shroud recreated, artificially and imperfectly, the airflow that the propeller blast and slipstream had provided in an airplane. This worked, but it came at a cost. The fan consumed a significant fraction of the engine's power that could otherwise have driven the tank, so the engine effectively had to cool itself by spending part of its own output. The fan and shroud added weight and complexity, and the cooling was never as good as the natural airflow of flight, so the engine ran hotter and was more sensitive to anything that obstructed its airflow, such as the dust of the desert, which clogged the cooling passages and the air cleaners and made the cooling problem worse. The air-cooled engine in a box was a workable solution, but it was a compromise piled on a compromise, an engine designed for one cooling environment, forced to operate in a completely different one. The radial configuration created a second major problem for the tank, and this one was about shape. A radial engine, with its cylinders arranged in a circle, is short in the direction of its crankshaft but large in diameter. The R-975 was about 45 inches in diameter, nearly 4 feet across. When you install an engine like this in the rear of a tank, with its crankshaft running horizontally toward the front of the tank to drive the transmission, the large diameter of the engine determines how tall and how wide the rear of the tank must be. The engine compartment had to be tall enough to contain the full circle of cylinders, and this height propagated forward through the design of the tank. This is one of the reasons the Sherman was a tall tank, taller than its German and Soviet counterparts, and the height was a real tactical liability. A taller tank is a bigger target, easier for the enemy to see and to hit. A taller tank presents more surface area to be armored, which means either more weight to armor it all, or thinner armor spread over the larger area. The Sherman's height became one of the standard criticisms of the design, and a significant part of that height traced directly back to the radial engine in its tail. To clear the engine and its drive shaft running forward to the front-mounted transmission, the whole vehicle had to be built up around them. The Sherman's silhouette, which German gunners learned to recognize and which Sherman crews learned to curse, was shaped in part by the decision to use a radial aircraft engine. The engine that was so compact in one dimension, so short front to back, was so large in another dimension, its diameter, that it pushed the entire tank upward. A purpose-built tank engine, long and low, would have allowed a lower tank. The radial, born for the airplane, made the Sherman stand tall, and standing tall in front of a German anti-tank gun was not where any tank crew wanted to be. There was a third peculiar problem with the radial engine in a tank, and it is one that the popular histories almost never mention, but that every R-975 crew knew about intimately, because getting it wrong could destroy the engine. The problem was hydraulic lock, and it came directly from the radial circular arrangement of cylinders. In a radial engine, some of the cylinders point upward and some point downward because they are arranged in a full circle. When the engine is running, this is not a problem, but when the engine sits idle for a period, gravity goes to work on the oil inside it. Oil drains downward, and it collects in the cylinders at the bottom of the circle, the lower cylinders, pooling above the pistons. Now, a liquid cannot be compressed. If too much oil collects on top of a piston in a lower cylinder and the engine is then started and that piston tries to rise on its compression stroke, it meets a slug of incompressible oil that it cannot squeeze. The piston is driven up against a solid column of liquid and something has to give. The result can be a bent connecting rod, a cracked cylinder, or other catastrophic damage. This is hydraulic lock, and it was a real and present danger with the R-975. The procedure to prevent it was a ritual that every tank crew with a radial engine had to perform. Before starting the engine, especially after it had sat for a while, the crew had to turn the engine over by hand, rotating the crankshaft through several revolutions to push any pooled oil out of the lower cylinders, past the rings or out through an open spark plug hole, before it could do damage. Only after the engine had been turned over and confirmed free of hydraulic lock was it safe to start. Forget this step or do it carelessly, and you could wreck the engine on startup. It was one more burden that the radial configuration placed on the men who operated and maintained these tanks, a burden that no inline or V engine imposed, a direct consequence of putting a circular aircraft engine in a ground vehicle. The company that actually built the R-975 for tanks was not Wright, which had designed it, but Continental Motors. And the choice of Continental tells you something about how the American engine industry was organized for war. Continental Motors was a Detroit engine manufacturer with a long history of building engines for other companies, engines that went into the cars and trucks and equipment of manufacturers who did not build their own engines. Continental was, in a sense, a specialist in building engines to other people's designs in quantity. The Army had already been using Continental's smaller R-670 radial in its light tanks, so Continental had experience with radial engines in armored vehicles. When the Army needed the larger R-975 built in quantity for its medium tanks, it chose Continental to build it under license from Wright, beginning in 1939 for the M2 medium tank and then for the M3 and the M4 Sherman that followed. The arrangement made sense. Wright was overwhelmed building R-975s and larger engines for aircraft, which was the priority. Continental had the manufacturing capacity and the radial experience to take over production of the R-975 for ground vehicles, freeing Wright to concentrate on aircraft engines. And Continental did the job on an enormous scale. Against the roughly 7,000 R-975s that Wright built for aircraft over the engine's whole career, Continental built more than 53,000 for tanks and other armored vehicles, more than 7 times as many. The R-975, an engine that had been a modestly successful civil aircraft engine, overshadowed in the aircraft market by Pratt & Whitney's WASP Jr., found its true mass production career not in the air but on the ground, built by Continental, powering the tanks of the United States and its allies by the tens of thousands. Continental's versions for armored vehicles, the R-975C1 and the improved R-975C4, were the engines that actually went to war in the Sherman, and they were Continental's product, built to Wright's design in numbers Wright never approached. Let us be precise about what the R-975 actually delivered in the Sherman, because precision is where honest assessment begins. The Continental R-975C1 was a 9-cylinder, 4-cycle, air-cooled radial displacing 973 cubic inches, about 16 liters. It had a bore and stroke of 5 inches by 5.5 inches and a modest compression ratio of 5.7 to 1, suited to the 80-octane gasoline it burned. In the C1 version, it produced about 350 net horsepower, and in the improved C4 version, about 400 net horsepower, with corresponding net torque figures of around 800 and 940 pound-feet. The engine weighed about 1,137 pounds dry, which was light, far lighter than the GM twin diesel that weighed over 5,000 pounds. It used a magneto ignition, like an aircraft engine, with no battery required to keep it running once started. These were respectable numbers, but they revealed the engine's limitations in the tank roll. The R-975 was, by the honest assessment of those who know the Sherman best, a solid and reliable tank motor, but not an ideal one. It was a little underpowered for the weight of the Sherman, which grew heavier as the war went on and more armor and bigger guns were added. And because it was an aircraft engine, it made its power at relatively high engine speeds, which meant it had to be revved up considerably to get the heavy tank moving, unlike a diesel or a big lazy V8 that made strong torque at low speeds. The Radial's torque characteristics were not ideal for the stop-and-start, low-speed hill-climbing work of a tank. The engine had to be worked hard, run at high revolutions to move the Sherman, which made it noisier and increased wear. It was, in the end, an aircraft engine doing a ground vehicle's job, and while it did that job adequately, it never did it as well as an engine designed for the job would have. It was good enough, it was not great. And good enough, available immediately in huge numbers, was what the war needed first. No account of the Sherman's engines can avoid the question of fire, the grim reputation the Sherman acquired, the nickname Ronson that some attributed to it, after the cigarette lighter that lit every time. It is worth addressing honestly because the popular understanding of it is largely wrong, and because the R-975's role in it is misunderstood. The Sherman did have a reputation for catching fire when hit, and early in the war this reputation had some basis, but the cause was not primarily the engine. The main cause of Sherman fires was the ammunition, the propellant in the main gun rounds stored in the hull, which could be ignited when a penetrating hit sprayed hot metal into the fighting compartment. When the ammunition propellant caught, the fire was catastrophic. The fix, when it came, was wet stowage, storing the ammunition in water-jacketed bins that dramatically reduced the fire risk, and this fix had nothing to do with the engine. But the R-975 did contribute to the fire risk in one specific way, which was its fuel. The R-975 burned gasoline, which is volatile and flammable, and a gasoline-fueled tank that takes a penetrating hit has a fuel that can ignite more readily than diesel. This was a real disadvantage of the gasoline engines compared to the diesel-powered M4A2, whose diesel fuel had a higher flash point and was less likely to ignite from a spark or a hot fragment. The Soviets, who received the diesel Shermans, valued exactly this characteristic. But the gasoline fire risk was a property of all the gasoline Sherman engines, the R-975, the Ford GAA, the Chrysler Multibank, not the R-975 specifically, and it was secondary to the ammunition fire problem in any case. The R-975 was no more fire-prone than the other gasoline engines, and the Sherman's fire reputation was driven mainly by ammunition stowage, which was eventually solved. The honest accounting is that the R-975 shared the general gasoline fire risk, that this risk was real but secondary, and that the Sherman's fire reputation was largely fixed by changes that had nothing to do with the engine. The engine was a compromise, but it was not the fire trap that the legend sometimes suggests. One of the most interesting and least known parts of the R-975 story is how much effort went into improving it over the course of the war, an effort that turned a marginal tank engine into a merely adequate one through sheer persistent engineering. The Army and Continental produced a detailed program of ordnance development for the R-975, working through the engine's problems one by one, year after year. They improved the cooling, they improved the reliability, they addressed the wear problems, the maintenance burdens, the various failures that emerged in service. By the time they were finished, the R-975 had been so extensively modified that it was, in the words of one expert assessment, almost a new motor compared to where it had started, though still not a great tank engine even then. This relentless, unglamorous development work is a side of wartime engineering that rarely gets attention because it produces no dramatic breakthrough, no single moment of triumph. It is just the patient, grinding work of taking an imperfect thing and making it less imperfect, a little at a time, fix after fix, version after version. The R-975C1 became the R-975C4 and other variants, each one a little better than the last. The engine never became excellent, never became the equal of the purpose-built Ford GAA, but it became reliable enough and good enough to soldier on through the entire war and beyond. And this incremental improvement mattered because the R-975 remained in service in large numbers throughout the war, and every improvement made thousands of tanks a little more reliable, a little more durable, a little more capable. The work was not glamorous, but it was real, and it reflected a kind of engineering virtue that the dramatic stories overlook, the virtue of patient improvement, of taking what you have and making it work, of refusing to give up on the imperfect tool because the perfect tool is not available. The R-975 ended up powering an extraordinary range of armored vehicles, far beyond the Sherman, and this ubiquity is a measure of how essential the engine was. It powered the M2 medium tank, where it began. It powered the M3 Lee and Grant medium tanks that fought in the desert. It powered the M4 Sherman in several of its variants. It powered the Canadian Ram tank, built on the M3 chassis. It powered the M7 Priest self-propelled gun, the mobile artillery that gave American and British forces their armored field artillery. And it powered, in a final irony, the M18 Hellcat tank destroyer, the fastest tracked armored vehicle of the war, where the same radial engine that made the Sherman tall and ponderous helped make the lightweight Hellcat extraordinarily fast. The R-975 was the common heart of a whole family of American armored vehicles. This ubiquity had a logistical logic to it. Using a common engine across many vehicle types simplified the supply of spare parts, the training of mechanics, and the management of the supply chain. A mechanic who knew the R-975 could work on a Sherman, a Lee, a Priest, or a Hellcat. The spare parts for one were the spare parts for all. In a war where logistics mattered as much as combat performance, the commonality of the R-975 across the armored fleet was a real advantage, even if the engine itself was a compromise in each application. The R-975 was the standard, the common denominator, the engine that was everywhere, and its very ubiquity made it valuable in ways that went beyond its performance in any single vehicle. The R-975 outlived the war, and its afterlife is a small testament to the fundamental soundness of the design that Charles Lawrence and Sam Herron and the Wright engineers had created. After the war, Continental continued to produce its own versions of the R-975 into the 1950s, and the engine returned, in a sense, to its origins, to the air. Post-war R-975 engines, improved versions producing as much as 550 horsepower, powered a generation of early helicopters, the Piasecki and Cayman machines that the Army, Navy, and Air Force used for utility, rescue, and anti-submarine work. The engine that had been designed for fixed-wing aircraft, then diverted to tanks, found a third career powering helicopters, its air-cooled reliability and compact form once again proving valuable in a flying machine. The engine's journey from civil aircraft in the late 1920s through the tanks of the Second World War to the helicopters of the 1950s is a remarkable arc for a single engine design, and it speaks to the basic quality of the underlying engineering. The R-975 was never the best engine for any of these jobs, perhaps, but it was good enough for all of them, reliable and adaptable and well-proven, the kind of sound, dependable design that finds use across decades and across applications. Surviving R-975 engines can be seen today in museums, the Smithsonian's National Air and Space Museum among them, displayed as aircraft engines with little hint of the tens of thousands of their kind that ground across the deserts and the hedgerows and the islands in the backs of tanks. The lesson of the R-975 is a lesson about the value of the good enough solution that is available now as against the perfect solution that is available later. The R-975 was not the best tank engine. The Ford GAA was better in almost every way. more powerful, better suited to the tank role, more advanced. But the Ford GAA was not available when the war began, and the R-975 was. The R-975 had been in production for years, was proven and reliable, could be built immediately in huge numbers by Continental, and could be put into tanks right away. The perfect engine that arrives after the crisis is worth less than the adequate engine that is there when the crisis hits, and the R-975 was the adequate engine that was there. This is a lesson that runs counter to the way engineering excellence is usually celebrated. We celebrate the breakthrough, the elegant solution, the best design. But wars and many other human endeavors are often won not by the best solution, but by the adequate solution that is available in time and in quantity. The R-975 was the engine that powered the Sherman through El Alamein and Tunisia and Sicily and the early fighting in Italy and Normandy. The engine that was there when the American tank program most needed an engine, any engine, that worked and could be built in quantity. It was a compromise, an airplane engine in a box, tall and a little underpowered and burdened with the quirks of its radial configuration. But it worked well enough in enough numbers at the right time. And working well enough in enough numbers at the right time is, in war, worth more than perfection that comes too late. The R-975 was the unglamorous workhorse that did the job while the thoroughbreds were still being bred. And the job it did was essential, even if history has chosen to remember the thoroughbreds and forget the workhorse. In a war decided by what was available was an airplane engine, and so an airplane engine went into the tank. The Continental R-975 was a radial, 9 cylinders arranged in a circle around a single crank throw, air-cooled, designed for the open sky and the rush of the slipstream, and it was dropped into the sealed steel box of a tank's engine compartment where there was no slipstream and made to cool itself with a fan that ate its own power. It was tall, and it made the tank tall, and the tall tank was a bigger target. Its lower cylinders filled with oil when it sat, and the crews had to turn it over by hand before every start or risk wrecking it. It had to be revved hard to move the heavy tank because it was an aircraft engine that made its power high in the rev range, not a tank engine that made torque down low. It was, in every way, a compromise, an engine doing a job it was never designed for. And it carried the American tank program through its most desperate hour. When the Sherman first went to war, the R-975 was the engine in its tail because the Ford GAA was not ready, and the other engines were being shipped to Allies. Continental built more than 53,000 of them, 7 times what Wright ever built for aircraft, and they powered the Shermans and the Lees and the Grants and the Priests and the Hellcats across every front of the war. The engine that everybody was trying to replace was the engine that was actually there, doing the work, while everybody waited for something better. It was born from the stubborn conviction of Charles Lawrence, the outsider who believed in air cooling when the whole industry doubted him, and had ended up in places he never imagined, grinding across the desert in the back of a tank. In a war fought between industrial systems, the system that could reach into its aircraft industry and pull out a proven engine, license it to a specialist manufacturer, and build 53,000 of them to power its tanks while it developed something better, was a system flexible enough to win. The R-975 was not the best Sherman engine. It was the first and the most numerous and the one that was there when it mattered. It was an airplane engine in a box, and it was good enough, and good enough available now in quantity, beat perfect available later every time. That was the whole point of it, and that was enough. In a war decided by what worked, the airplane engine in the tank worked well enough and long enough and in enough numbers to help carry the Sherman from the desert to the heart of Germany. It was the compromise that did the job, and the job in the end got done.